Hey, this is another chapter on machines, chapter 24. In this chapter, we'll be discussing mostly milling operation, and then we will spend some time on other machining processes like broaching, sewing, filing, and we'll lastly discuss some uh, types of gear manufacturing. It's quite difficult, so we have a brief section on how to manufacture different types of gears. And milling is again, as in the case of lathe machines or turning operations, it's quite versatile. If you have a milling machine, you can perform various operations, and it is much more actually versatile than turning machines, I can say, since we can manufacture not only round shape but much more complicated shapes can be machined on milling machines. For instance, if you look at these shapes, they are complicated than the round shapes we can machine on the lathe machines. You see, we can manufacture such gears, we can have such extra features, even such much more complicated parts, having threads inside and having some grooves, horizontal grooves, and having some pockets. They are possible with the help of milling machines. And there are many types of these machines, and these days we prefer to use computer numerical control type of milling machines. We will discuss them in the other section, other chapter, but I can say that with the help of them, you can machine more complicated products having high quality surfaces. So if your design requirement, manufacturing requirements are high, then you may go with milling machines, especially CNC milling machines. And here we will first discuss the types of milling. There are different types. Peripheral milling, we have face milling, we have end milling, and other slotting types of milling operations we have. The most important ones are peripheral and end milling. We will spend some time on peripheral milling, but I may show you first some pictures of different milling processes. For instance, this is face milling, and as the name implies, with the help of this milling process, we are removing material from the top surface. And you can see some specific milling cutters. And then we have end milling, or sometimes we may call it as shoulder milling. You see, we have a specific tool. It goes into the material workpiece and removes some material sometimes from the shoulder, but even it can go into the workpiece and open some types of pockets. We have further profile milling, slot milling. We are opening such slots, thinner or larger. Then we may have some grooves, groove cutters. And lastly, it's almost the same with tapping. We may sometimes be using the term thread milling. Man, the thing is that we can perform all these different operations on the milling machines. Now I will focus on the first type of milling operations. It is peripheral milling, and it's sometimes also called as plane milling. And I will show you a picture of this simple milling operation. As you see, the axis of rotation of this milling cutter is actually parallel to the machine, parallel to the surface to be machined. So this is a main requirement of the milling process if you are going to name it as an peripheral milling. And if the width of this cutter is actually larger than the width of the workpiece, then we simply call this process, the milling process, as slab milling. So this is the only requirement for the slab milling operation. And obviously on this milling cutters, on this cutters actually especially used for peripheral milling, we have cutting edges, or if you are using inserts, then we may say that you have actually single point cutting tools installed on the edges of your cutting tool. And in peripheral milling, we may sometimes have straight cutters, having actually cutters having straight teeth or having helical teeth. Helical teeth are very similar to the actually teeth profile we have on the drills, but the straight teeth, as the name implies, it's not rotating around the axis. We have straight teeth along the cutter, and the difference is that with the straight cutters, straight milling cutters, we do orthogonal cutting, but with helical teeth, we do an oblique cutting operation. And for most of the time, we prefer to do prefer to use helical teeth, since with the help of them, we at least one or two actually teeth are always in contact with the workpiece during the machining operation. But if you use straight type of milling cutters, then what will happen? If you assume my fingers as the teeth, then you see while we are rotating around the workpiece, only one teeth is only one tooth is always in contact with the workpiece. But if it's helical, then we will probably have at least two or maybe more teeth in contact with the workpiece. And with the help of this more contact, we are not going to have uninterrupted cutting. Actually, we will not have actually and impact forces on the workpiece, but we will always be in contact with the workpiece, and machining will be much more smooth, and we are not going to have too much vibration or chatter. So that's why for better quality surfaces, for lower surface roughness values, we prefer to use helical teeth instead of straight teeth. Now I'm going to discuss two types of peripheral milling. These are called conventional milling and climb milling. I will be talking about many properties of these types of milling operations. Please make sure that you prepare a kind of a table and then write main properties of these milling operations. But I'm not going to do that. I will be talking about these properties one by one. And first, I want to show you a schematic showing the main difference between conventional milling and climb milling. So the main difference is actually in terms of the direction of cutting operation. In all of these, in conventional and climb milling operations, right now in our sketch, workpiece is actually moving to left. But if you look at the cutters, they are rotating in different directions. In the conventional milling, this milling cutter is rotating in counterclockwise direction, but in the climb milling, it's rotating in the clockwise direction. But if you focus into the cutting zone, you can say that the cutting action is actually in the opposite direction of the motion of our workpiece. But in the climb milling, the cutting action, the cutting speed is in the same direction with the motion of our workpiece. So this is one difference between conventional milling and climb milling. And other difference is in terms of the chip thickness. Now let me try to annotate it for you. So if you look at here, at the beginning of the process, we have a very thin chip generated, but it gets larger as this part is removed from the workpiece. On the other hand, if you look at climb milling, at the beginning of the operation, we have a thicker chip, but once it's being finalized, finished, then we have the thickness of this chip reduced. So this is another difference I can say. So in summary, in the conventional milling, once we start to remove material from the workpiece, the thickness of the chip is lower, but it gets thicker as we rotate this cutter. And it's not the same in the climb milling. In climb milling, we start with a thicker chip and then it gets thinner once our actually teeth are going into the workpiece. So I can say that since these teeth are actually facing the dirty surfaces, unmachined surfaces, so the quality of this workpiece, unmachined workpiece, highly affects the life of our cutter. So it's probably there are lots of dirt on the surface, and once you're hitting on the surface with your teeth, then it may harm your cutting teeth and may make them dull actually, and you need to do some resharpening operation frequently. But on the other hand, if you look at conventional milling case, we are actually in contact with the machine surface. So since it's machined, we can assume that that surface is much more clear than the surface actually we are facing in the climb milling. So I can say that you can use the milling cutter in the conventional milling more than the milling cutters you are using in the climb milling. So the tool life is much different in these two different types of operation. Another difference between conventional milling and climb milling is actually the amount of force we need to apply to hold these workpieces in place. For instance, if you look at the conventional milling, once actually our teeth engages with the workpiece, they are actually trying to move our workpiece upwards. So that's why actually we need to fix it properly. We need to apply with more force to hold these workpieces on the plate. But you may use less force to hold these workpieces on the table, since our cutting teeth actually are pushing our workpiece into the table. So we don't have a tendency to move this workpiece out of the table. So with less force, you can hold your workpiece on the table. Another thing we have is about actually the backlash, gear backlash. I'm assuming that you know what a backlash is. If you have a gear pair, and since we cannot have a continuous contact with the teeth of gears, so at the point we may have we cannot transfer the motion, and this is highly important if you, especially if you are changing the direction of motion. So once you change the direction, that means we will be losing the contact between the teeth, and we will not be able to transfer the motion to different mechanical components. And it's highly important, actually, in climb milling. If you cannot eliminate backlash in the underneath mechanism of your table, then you will have problems in the positioning of your table more in the climb milling. But it's not a big issue in the conventional milling. Even though you have some amount of backlash, that will not be a big problem in the conventional milling operations. Let me go back to this part and check whether I have talked about all these issues, as these are things I mentioned. And with conventional milling, the quality of the surfaces is much better, and that's why for about most of the time we prefer to use conventional milling, and our the life of our tool will be longer, and we will be having high quality surfaces. But the thing is that the sharpness of the teeth should be better, since if it's not sharper, then your cutting edges cannot remove material. And once you cannot remove material, then things will develop and you will have more problems. You may even break the edges of your cutting tool, and this may result in a catastrophic failure. And I think the rest is the things I mentioned. Yes. So now let's look at some parameters, milling parameters. The first one is the cutting speed, and as you know, the cutting speed actually the speed at this cutting zone. And if you look at here in the conventional milling, our cutting speed is in the opposite direction of our workpiece motion. And how we determine it? If you know the rotational speed of your cutter, then you can simply multiply with the diameter of your cutter and pi and determine the cutting speed. Then I can talk about the machining time or the cutting time, how we determine it. Let's have a look at the sketch. This is our workpiece, and assume that we are trying to actually remove this much of material. This upper part of the material is going to be removed from the workpiece. It is here, this portion. This portion is going to be removed from the workpiece. And what are the dimensions of it? Its length is L, its depth is D, and we have actually another width into the page or into the screen. This is W. So if you multiply all these, you can determine the volume of this material to be removed. And on the other hand, how we calculate the time, we can only consider the length and the speed of our workpiece. So what are the lengths? We have the workpiece length L, and we also need to include LC. What is LC actually? It is the distance between the center of our cutter and the tip of the cutter once it's actually touches the workpiece. So that's why we need to include it in the equation, since once it touches the workpiece, we start the machining process. So that's why we are summing L and LC together. This is the total motion we have, distance we have during the material removed from this workpiece, and then we need to divide it by the speed of our workpiece, which is V. So once you do this division, you can obtain the cutting time T. And on the other hand, material remove rate is not complicated. This is the amount of material we are removing, the volume of the material here, LWD, and if you simply divide it by the cutting time, you can obtain the material removal rate. And if you assume that your LC is highly small compared to the length of your workpiece, then you can neglect it, and instead of having this division, you can have it simpler, simplified material removal rate equation. It is equal to the width of the workpiece, depth of the cut, times the speed of your workpiece. So by simply multiplying these three terms, you can obtain the overall material removal rate in this peripheral milling operation. So for different milling operations, you need to come up with different equations. This is valid for peripheral milling operation. This is the summary. So if you determine the cutting force, then you can multiply simply with the radius of the milling cutter, determine the torque, and once you know the torque again, as in the case of a turning operation, you can multiply with the angular speed and determine the power requirement of your milling operation. Make sure that you have a look at this example here. Now we discuss the first type of milling operation, peripheral milling. Now I will briefly talk about other milling operations. The second one is face milling. As I showed you in this picture here, face milling is about removing material from top surface of the workpiece, okay? And this time, as opposed to the peripheral milling, our axis of rotation of the cutter is perpendicular to the surface which is to be machined. In the peripheral milling, it was parallel, but this time in face milling and end milling operation, the axis of rotation is always perpendicular to the surface to be machined. And here in this part, actually, our aim is mainly improve the surface quality, the top surface quality. For that purpose, actually, we use face milling operation. And in face milling, the marks of our inserts or teeth are highly important, since it's the face actually we are always looking at. So we don't want to have such marks on the surface. And there are some different ways to remove these marks, but it's almost inevitable. You will mostly always have some marks, but the thing is that you can find some ways to decrease the depth of these marks. Since if the depth is decreased, then it may be less effort. You can eliminate them after the part is ready, or if the depth is not too much, then you can directly use it in your assembly or other kind of applications. And as in the case of peripheral milling, again, we have decline milling and conventional milling, but the idea is the same. In decline milling, as you see, the motion of our workpiece is in the same direction with the cutting operation, but in the conventional milling, again, the directions are opposite. Let me talk about this markings a little bit. So the markings actually highly depend on the type of inserts, type of cutting tools you are using. For instance, if you have such radius at the corner of your insert, then you're going to have such marks. But if you have flat corners, then again you're going to have high surface roughness. So you need to find something in between. This is a common solution. We have small radius here and we have large radius at the other end. So if you have it, then you're going to have much better surfaces. The surface roughness will be reduced. You can see other cases here. So the radius is highly important. It determines this overall waveform. So depending on your case, on your requirements, you should try to find the best type of actually insert so that your resulting quality will be much better. Now let's briefly talk about end milling. End milling is actually one of the most common milling operations, and I may show you some examples while we are having the synchronous sessions in the upcoming days. And there are different types of end mills. You see, they're all end mills. We can have various sizes. Their tips might be a bit different. You may have circular end mills, flat end mills. But the thing is that in end milling operation, we are actually removing material with the bottom actually side of this tool and also with the side edges of the tool. So we are removing more material with these end mills, and the thing is that they are mostly used to actually open some pockets, remove material from the side surfaces. So they are quite useful in many in most of the milling operations. We do at least one end milling operation. Now let's have a look at other types of milling operations. So we discussed peripheral milling, end milling, and face milling. Now we'll be talking about least commonly performed milling operations. We have straddle milling. As the name implies, actually, we have a kind of an arbor here, and this on top of this arbor, they have mounted two different actually milling cutters. So at the same time, with a single motion, we can remove material from the two sides of the workpiece, and that's why it's called as straddle milling. Then we have fore milling. Again, we are using an arbor. So on top of this arbor, we are mounting a milling cutter. So you see it has a special shape, and with the help of the cutting edges of this cutter, we can obtain such special forms. It's very similar to forming operation on the lathe machines. Then we have very similar processes, slotting and slitting. They are almost the same. The difference is that in the slotting operation, the width of the groove is a bit larger, but in the slitting, this width is quite small, thinner, but the fundamentals are the same. And as you see in all of these processes here, we are using a kind of an arbor. So this is an kind of a tool holder, a highly popular tool holder in milling operations. But we also have shank type of milling cutters. What we do in these, we cannot actually change the cutter, but the cutter itself has a kind of a shank upwards, and we can easily mount this shank into our spindle and then do the machining operation. Okay. And depending on your requirements, actually, you may come up with your own milling cutter, and then you can produce the shapes in a maybe shorter time in a much more economical way. Let me talk about briefly on T-slot milling. It's a very special process, or it's called as T-slot cutters. You see, this is actually opening T-slot we are going to have after this operation is completed, but we cannot obtain it in a single motion. What we do, we first open such a hole, and then once it is prepared, opened, then later we use our milling cutter, a T-slot cutter, and with the help of it, we can obtain this part. And after this operation is over, we will obtain a kind of a T shape here. And if you remember, these are highly important, especially in tables, and you can easily mount some work holding devices inside, some fixture. So in almost all type of machines, milling machines, sometimes different drilling machines, we use such T-slots to fix our work pieces. And this T-slot has actually have many cutting edges. It's removing material from this side, top side, bottom side, and also from the side surfaces, side edges. So its removal rate is a bit higher compared to other types of cutters. These are all I can say about the types of cutter holders. And now let me briefly talk about the types of milling machine we are using. As I said at the beginning, again, milling machines are highly versatile. You can do many operations on this machine. Even though it's not a CNC type, you can still do many machining operations on the milling machines. And these days we have the CNC versions of them, and we love to use the term CNC machining center instead of CNC milling centers or CNC milling machines, since we are performing many machining operations. That's why it's better to use the term machining center. What we can do on these machining centers, we can do milling, we can do drilling, boring, tapping, since we have relative rotational motion, and also we can move our workpiece on the plane. So once we have this kind of freedoms, we can perform various machining operations. And the advantage is that they're highly repeatable, their machining accuracy is quite high compared to the other types of machines. So what are the types of these machines? The first one is column and knee type. It is the conventional type of milling machine. And as the name implies, we need to have a column and a knee. And I will show you the fundamental of this one. Let's focus on here. This is our column, and we have a knee, and this knee is moving over the column. And as in the case of drill presses, we have a base, and on this knee this time we have a saddle. So the knee is moving actually in Z direction, and then we have a saddle, it's moving in Y direction, and we have on top of the saddle we have a table, it's a work table. This is moving in X direction. So we have three translational motion. With the help of knee, we are moving in Z. With the help of saddle, we are moving in Y. And with the help of our work table, we are moving in X direction. So with the help of them, we can position our workpiece any place we like. And then what we do, we need to have a kind of a hat installed with an electric motor and a spindle. And at the tip of the spindle, we need to have a cutter. And this cutter is rotating at high speeds. And if you have this actually had in a vertical orientation, then this is called simply vertical spindle column and knee type milling machine. But if it's horizontal, then it is simply called as horizontal spindle column and knee type milling machine. The thing about the horizontal milling machine is that we need to have a kind of an overarm. So if you look at the vertical one, we don't need to use such an overarm, but in order to stabilize this cutter, this peripheral milling operation, we need to also hold it from the other side. Otherwise, the stiffness will be lower, we will have vibration again, chatter, and the quality of the surface will be lower. So they solve this problem with the help of the overarm, but the rest, the fundamentals of milling process is the same with the vertical spindle column and knee type of milling machine. So I think I talk about all these issues. Then we have some other types of Kalmani type machines, but the fundamentals are the same. If you can somehow rotate your work table, then it's called as an universal Kalmani type machines. Then we have bed type milling machines. The fundamentals are highly similar, but these are quite larger machines. I will show you some example videos about these machine types. But the main difference is that with respect to the Kalmani type, we don't have a knee actually this time. We don't have a knee, but we have a large bed, and all the motions are actually done on this head part. The tool is moving in all the directions. Another thing about the bed type milling machines is that depending on your requirements, you may have not just a single spindle, but you may have multiple spindles so that you can perform many operations at the same time or machine more products at the same time to increase your overall productivity. Then we have other types of milling machines, but not as frequently used as the previous ones. We obviously have CNC type of machining centers. We have planer type milling machines. These are highly similar to the bed type. And the thing is that the cutter is actually moving in this translation direction, in this X direction, in a reciprocating manner, or if the size of the bed is not too much, bed might be moving in that direction. But they are quite similar to the bed type of milling machines. And then if your table is rotating on an axis, then we can call your milling machine as a rotatable milling machine. And these days we have CNC milling machines, and they are sometimes called as profile milling machines, especially multi-axis version ones, since they can open any profile with the help of their more degrees of freedom. It's an example of an CNC type of milling machine. So this is actually one of the earliest versions of CNC type of milling machine. But we have now these days much more complicated, much more powerful CNC milling machines. And on top of these milling machines, sometimes you need to use special fixtures, special devices. The workpiece, the placement or the holding of the workpiece is highly important. It should be stationary, and for that purpose, you may design your fixtures yourself or purchase some available fixtures from markets and try to mount your workpieces inside. And you need to maybe using T-slots on your table so that it will be easier to mount your fixture on that table. And if you want to actually produce some kind of gears or complicated profiles having special angles, then you may need to use universal dividing heads. We are going to install this head actually onto the table, and then with the help of the settings there, you can rotate your workpiece to specified angles and then do the machining operation.